100 billion messages a day. That is WhatsApp. But plenty of apps move huge traffic. So hold that number, because it is not the part that should stop you. This is a single WhatsApp server held 2 million live connections at once. Not 10,000, not 100,000. 2 million on one machine. Most systems buckle long before they get close. Sit with how impossible that sounds for a moment. Now the twist. The company that pulled this off, at the point Facebook paid $19 billion for it, was about 50 people. Total. Every discipline, iOS, Android, servers, operations. 50. So how? Not a giant team, not a trendy stack, a language almost nobody uses. One built for telephone switches in the 1980s. This is the story of Erlang. Great engineering is not about doing more. It is about needing less. When an app explodes in growth, the usual response is to hire. You add services. You split the team into squads. Coordination cost climbs, complexity climbs, and your headcount chart looks like a hockey stick. WhatsApp did the opposite. As users went from millions to hundreds of millions, the team barely moved. When they hit 450 million monthly users, the infrastructure group was around 30 engineers. When Facebook bought them in 2014, the whole company, every discipline, iOS, Android, servers, operations, was roughly 50 people. So the real question is not how a chat app works. You could sketch that on a napkin. It is this. What lets 50 people carry a load that would sink 1,000? You cannot out-hire this problem. You can only out-design it. And every design choice WhatsApp made traces back to one decision about concurrency. Erlang was not designed for chat apps. It was designed for phone calls that must not drop. In the 1980s, Ericsson had a problem. Telephone switches had to stay up. Not mostly up, always up. The target was 5 nines of availability. Sit with what that means. A full year, 365 days. And the system is allowed to be down for about 5 minutes. Total. A phone network cannot pause for a deploy. It cannot crash because one caller sends something strange. It has to handle millions of simultaneous conversations, keep each one isolated, and recover from failures on its own. So Ericsson built a language around those exact needs. Concurrency first, fault tolerance as a built-in feature, not an afterthought. The ability to upgrade code on a running system without turning it off. Now picture a messaging app. Millions of simultaneous conversations, each one isolated. Recover from failure without going down. WhatsApp's problem in 2010 was Ericsson's problem in 1986. The tool already existed. Almost nobody thought to use it. Here's the idea that changes everything. Give every user their own tiny running program. Most languages handle many users with threads that share memory. Threads are heavy. They fight over the same data. You need locks to keep them from corrupting each other. And locks are where concurrency goes to die. Erlang throws that model out. Instead of threads sharing memory, it uses actors. An actor is a lightweight process that owns its own private state and shares nothing. Actors never reach into each other's memory. They only send messages. One actor drops a message into another's mailbox, and that actor processes it when ready. No locks. No shared state to corrupt. In WhatsApp, this maps perfectly onto the problem. One process per connected user. Your phone talks to your process. Your process talks to mine by passing a message. If 1 million people are online, that is 1 million little processes, each humming along on its own, each isolated from all the others. And because these processes share nothing, they are cheap. Not 1 million operating system threads that would melt the machine, but something far lighter. Which brings us to the engine underneath. The magic is not the language. It is the virtual machine that runs it. Erlang code runs on something called the beam, and the beam does something most runtimes cannot. Its processes are not operating system threads. They are its own creation, and each one starts out weighing just a couple of kilobytes. You can spin up hundreds of thousands of them on a single server. Millions across a cluster. The beam schedules them itself. It does not wait for a process to politely give up control. It uses preemptive scheduling. It can pause any process, run another, and come back. So one slow or greedy task can never freeze the whole system. Every process also gets its own small slice of memory and its own garbage collection. So when one process cleans up its memory, it does not pause everyone else. There is no giant stop-the-world freeze across the machine. Here is what that actually buys you. The same machine that would choke on 10,000 operating system threads calmly holds 2 million of these processes. That is the difference between renting 100 servers and renting a handful, between a data center and a closet. 2 million live connections on one box, not because the hardware was exotic, but because the runtime was built to do exactly this. Massive concurrency was never bolted on. It was the whole point. Most systems try to prevent every error. Erlang assumes errors will happen and plans for them. This is the philosophy that sounds reckless until you understand it. It is called let it crash. In a normal code base, you wrap risky operations in defensive checks so the program never dies. That code piles up, it is hard to get right, and it is where a lot of bugs actually hide. Erlang takes a different stance. If a process hits something it cannot handle, let it crash. Because each process is isolated, one crashing does not take down the others. Your process failing does not touch mine, and watching over them are supervisors. Special processes whose only job is to notice a child crash and restart it in a known good state. Supervisors watch other supervisors too, all the way up. A tree that keeps itself alive. So watch what happens when one of those millions of processes dies. In most systems, this is the start of a bad night. An alert fires, someone scrambles, a page goes out at 3 in the morning. Here, the supervisor just starts a fresh process in its place. The others never notice. No cascade, no incident. The failure comes and goes, and the system heals itself before anyone reaches for a laptop. Add to that the ability to load new code into a running system without ever stopping it. And you can see how a tiny team keeps something this big alive. The system largely takes care of itself. By now you're probably waiting for the last trick. Every answer so far has been a clever piece of technology. The actor model, the beam, supervision trees. So there must be one more secret, right? Some final architectural sleight of hand that ties the whole thing together. Well, there isn't. The most powerful decision WhatsApp made was not technical at all. It was saying no. For years, WhatsApp did essentially one thing. Just send and receive messages. No news feed, no ads network, no games, no stories, no shopping tab, no timeline. While competitors bolted on feature after feature, WhatsApp guarded a tiny surface area with something close to stubbornness. This is the multiplier that makes the 50 engineer number real. Every feature you add compounds. Someone builds it, someone maintains it, and it brings new failure modes, new things to monitor, new surface area to secure. 1,000 small features quietly demand 1,000 small owners. WhatsApp refused that trade. They called it just enough engineering. Build only what the core problem needs. Lean on boring proven tools before writing your own. Automate only when you must. So how did 50 people do this? 2 answers, working together. A runtime that made massive concurrency almost free, and a team disciplined enough to keep the problem small enough for that runtime to carry. The technology bought them room. The restraint kept them from spending it. You will probably never rewrite your system in Erlang. That is not the point. The point is the pattern underneath it. Isolate your state instead of sharing it. Let independent pieces fail without taking the whole system down. And question your defaults. The database, the language, the architecture you reach for by reflex may not be the one your problem is actually asking for. The actor model did not stay locked inside Erlang. It lives in Elixir, which runs on the very same beam with friendlier syntax. It lives in Akka on the Java side, and you can feel its shadow in Go's channels. The ideas travel even when the language does not. But the real lesson is not about Erlang. It is about how great engineers think. When a system strains, the reflex is to add more people, more services, more moving parts. The rarer, harder move is to design, so you need less. Great engineers don't out-hire their hardest problems. They out-design them. So the next time something you're building starts to buckle, ask the WhatsApp question first. Not, what do I add? But, what could I make simple enough to not need at all? If that idea is useful to you, subscribe. There is a new system design breakdown every Thursday.